and it is a great pleasure. I'm really grateful to be here. And I have known Peter for about 10 years now. And like many of you were saying yesterday evening, Peter and Nancy's hospitality and kindness, it's never really just for an individual, it extends to your family as well. So every time I bring kids to Berkeley, for example, you have to take them to see Peter and Nancy. So found this picture, that's my daughter right there, having free reign in Peter and Nancy's living room. And I remember that I was kind of trying to control her movements a little, and Nancy was like, no, don't tell her off, just let her do whatever she's doing. So thank you, Peter, for working with me. It has been a real privilege to learn from you and to be kind of part of this extended academic family. Okay, so I'll get started with the talk. Let me just show you really quickly the title of the talk. This is Bootstrapping the Error of Oja'S algorithm. And in hindsight, when I was talking to one of my collaborators, maybe we should have called it something like online multiplier bootstrap for streaming PCA, because that's what Oja'S algorithm, that's the algorithm that I mean. That's what I'll hopefully make that more explicit. So this is joint work with my collaborators, Robert Lundy, who is a former postdoctoral scholar who is spending a year with Lisa and G at Michigan. He's right there. So if you have any hard questions, just ask him. Anyways, no, I'm kidding. So, yeah, and he will be joining the Washington University at St. Louis as an assistant professor in the fall. This is Rachel Ward. She's a professor in the math department at UT Austin. Okay. So here's the outline of my talk. I'll talk about streaming PCA and kind of get into distributional approximation and an online bootstrap to estimate that approximate distribution. What I also had here is simulations, and when I was practicing, I was going over, so I removed it. But if I have time, hopefully I'll talk a little bit about simulations as well. Okay. So let's talk about streaming PCA. So here is my setup. I have n IID mean zero random variables in d dimensions with covariance matrix sigma. And this is a very familiar objective function for PCA, because we are basically saying, find me a unit vector so that when I project all my data points on that, I'm maximizing variance. That's it, right? It's a non-convex optimization algorithm, and it's like one of the very nice examples of non-convex optimization algorithms where the surface is nice. So there are no bad local optima. Okay, so the thing is, you can also calculate the sample covariance matrix and look at the principal eigenvector of that, right? This is, the thing is, when D is really, really large, you don't want to calculate, what if I don't want to calculate that entire D by D matrix, sample covariance matrix? So what we are going to do is use stochastic gradient descent, okay, on that optimization objective. So if you do SGD, it's very simple. You are basically pretending I have one data point at a time, and I'm doing a derivative or gradient of that objective function, and I'm just moving with some gamma t scalar. That's essentially your learning rate. And you just keep updating your weights. This weight vector, this is d-dimensional, right? And it's essentially eventually going to converge to the V1, which is the principal eigenvector of your unknown covariance matrix. And of course, because everything is unit vector, you have to do a projection. So it's like a projected SGD algorithm, right? So the gamma t, there are lots of different learning rate schedules. You can do something that decays 1 over n and so on and so forth. And I'll talk about that in a bit. And the initialization is very simple. You just pick a unit vector uniformly distributed on the d-dimensional sphere. See? So this is Eric Oja'S algorithm. He introduced it in 1982. And in fact, that update has roots in something far earlier in Hebbian theory, which was introduced by Donald Hebb, who is a psychologist, and in his 1949 book on organization of behavior. So it's some of the things like Peter was saying yesterday, that stochastic gradient descent is such a workhorse algorithm for optimization, which has been there long time back. Okay. So what I'm going to do is now kind of get into the nitty-gritties of things. So our update, if you remember, was of that form. So we're going to unfurl that update, okay, and write down the Oja'S vector after I have seen n data points. What does it look like? Okay, so, and I'm going to call that V Oja'S, the Oja'S direction. So it looks like something like this. It's kind of like not nice looking. What's happening is you have a matrix product, okay, of n independent matrices. So it's I plus this is essentially my learning rate. I'm going to fix it at something, some like eta n over n. Eta n is going to be roughly like log n. Okay, we'll worry about that later. So I have this sequence of IID matrices. I'm doing a product, and then we are just taking a projection on this initial direction. That's my numerator. That's a d by 1 dimensional vector, right? D-dimensional vector. Denominator is just a norm. That's what it works out to be. Okay. Now, why should something like this work? When I looked at it, it was like, man, that looks complicated. So I'm going to do something very ad hoc and hand-wavy. We'll just look at the numerator, because if I take an expectation of the whole thing, it's not nice, right? It's a ratio. Let's just look at the expectation of the numerator. Everything is nice and independent. So you basically have identity plus some gamma, which is eta over n, sigma to the power n. So what that's doing is it's taking your sigma and it's kind of doing a matrix exponential. Okay, so so now the new eigenvalues of this are going to be something like e to the power eta times lambda I. Okay, so it's what it did is if you had lambda 1 minus lambda 2 as your gap, it just increased that gap a lot. And yes, I'm going to assume that lambda 1 is not equal to lambda 2 for this talk. Okay, so and now once you have done that, you multiply by u0, it's going to very nicely align with your principal eigenvector direction. So that's kind of what's going on here. Okay, right? So huge amount of work on streaming PCA and Oja'S algorithm in computer science and machine learning literature. And let me also talk, kind of give some notation here. Sigma is our unknown covariance matrix. V1 is principal eigenvector of sigma, and lambda 1, lambda 2 are the top two eigenvalues, and we are assuming they're separated. And the error, how do we measure error? So V Oja'S is like the Oja'S vector, which is coming out. We are going to calculate a sine squared error. Okay, so this is calculating the cosine square, 1 minus the cosine square. So if my sine square is 0, I'm very happy, because it's basically saying that I have found a vector which is sitting exactly aligned with my V1. Okay, so the sharpest rate was obtained by Jane et al., and there are many other papers. And what they show is that the error of the offline calculation, if I just had this big matrix, I calculated my sample covariance matrix, looked at the largest eigenvector, principal eigenvector, this method is going to sort of match that. Okay, even if I'm not getting to look at the entire covariance matrix at a time, and I'm just looking at one data point at a time. And in particular, the sine squared error is going to be something like 1 over n. There are caveats, of course, there are conditions. In particular, it's very strong condition. This xi transpose, the outer product matrix minus its expectation, which is sigma, operator norm has to be bounded almost surely. And you will see this condition nearly everywhere in all the papers on streaming PCA. And this is essentially saying that this is my learning rate schedule. And you can see the kind of thing you see in stochastic gradient descent, something like 1 over t, right? So, okay, so what are we going to do here? So what we were interested in was saying that, okay, so the sine squared error behaves roughly like 1 over n after seeing n data points. So what we wanted to see was, if I multiplied the sine squared error by n, does that stabilize? Okay, so essentially a distributional approximation of the sine squared error after like scaling it properly. And this is what we are going to show, that something like n times the sine squared error is going to behave like roughly a chi-square random variable. And again, I'm not being precise here. I'm just trying to give the intuition of what's there in the results. Okay. And then how do I estimate that distribution? We are going to do an online bootstrap. Sorry, is there a question? And in order to estimate the distribution, we'll do an online bootstrap. Okay, so that's kind of the two parts of the talk. Yes.
Go back one slide.
Yeah.
Where's the dependence on D? Or does this nu, which is an absolute constant, depend on D?
So this essentially is, you are assuming a lot of things. In particular, this V is kind of, I think, expectation of this thing squared. So it's popping up there, but you are assuming everything is, at least in the CS literature, you assume all of those things are constants. And so that's why you can actually get very strong rates like this. And even if D was exponential in n, even then this will work. But this is the key. Essentially, it's saying that you don't really have a high dimensional problem. There is a low dimensional problem hiding inside them. Right, so let's do that. So I want to actually go to the board here just really quickly and build some intuition with scalars. Okay, so our matrix product was something like I plus something times xi transpose. Forget for a second you have vectors and matrices. Let's make everything scalar because matrices don't commute. It's not nice to move things around. Let's just see what happens with scalars. Okay, so I'm going to write this down. Hope, can everyone see this? Yes. And in my case, E of xi is 0, E of xi square is sigma square. So what we are going to do is something very simple. We'll say that, oh, you know, let's write xi square as sigma square plus xi square minus sigma square. Let's expand this whole thing out. And this is just 1, I'm sorry. Okay, so once you do that, what you get is the first term. Of course, the first term is going to cancel out because it's 1 plus sigma square over n to the power n goes away. The first term that's left is something like a linear, an average of xi square minus sigma square. And then what you have is an average of pairwise terms, and then an average of 3 triples and 4 and so on. And I'm wondering if this reminds you of anything. So the very first term, of course, it's nice. It's IID, average of IID things. Second one looks horrid, but it's uncorrelated. If you take like if you think about, just look at it, eyeball it for a second, you will see that it's sum of uncorrelated things. Same for every term, and they are uncorrelated among each other. Right, so very reminiscent of the Hoeffding decomposition of U statistics. And the funny thing is, oops, sorry, my colleague was talking, Rachel was giving a talk about random matrices or Oja'S somewhere, and Bin was in the audience, and this was far before we were talking about this, and she asked, what's the connection with U statistics? So I don't know how you saw that, but there is this connection, right? So the first term is the Hayek projection. Right? You're basically saying, I have this horrid product looking thing. I'm going to try to project it down on a linear space of random variables, sums of functions of random variables. And this converges to a normal distribution and under appropriate condition. The second term is essentially of this form and so on and so forth. And because everything is uncorrelated, they are really easy to bound, right? The variance is very nice, just decomposes. Let's now get to matrices. Okay, so my Bn is the matrix product of that giant thing. I can do the similar Hoeffding decomposition there as well. And I'm going to call those terms T0, T1, and so on. So I'll show you the first one. T0, very easy, just expectation. Okay, so it's like I plus learning rate times sigma to the power n. Looks like this, just to visualize it. N matrices, all of them are the same. This guy, right, they're constant. Okay. All right. What about the second one? That is not very nice because now things don't commute. You have matrices, right? Before I could just move all the constant things together. So now what you have is this xi transpose minus sigma, which is kind of like the x square minus sigma square before in the scalar case. What will happen is you will replace that sequence of constant matrices plug it in 1, 2, 3, 4 and get n things and take an average of them. So ends up being something like eta n times an average of independent mean zero matrices. Okay? So the structure is very much there. The analysis just gets messy because things don't commute. Okay? So now, so how do we put, and I also had a slide with T2, it just looks horrid because you start putting in pairs of random matrices, different places. So now the thing is the sine square error can be also expressed as this. Okay, it's a ratio of two things. And in the numerator, what you have is a norm square of u bn times u0. And what is u? U is essentially the orthogonal eigenspace to V1 of that covariance matrix sigma. Okay, so now once we have this, and this is not something we did, it's very well known, and this is what is used for the analysis in computer science typically and machine learning. So now the question is, how do I bring in where do I go from here? So all our focus is now on the norm of that vector. This is a d-dimensional vector, norm square of that. So, okay, so we are basically saying the first thing to do, the most natural one is like, oh, u0, just write it in the basis of all your d eigenvectors, right? We can do that, fine. Linear combination of the eigenvectors. And then you have to show that the norm is actually dominated by the projection along the principal direction. That's very important because we kind of didn't worry about any of that, did some calculations, had very suboptimal rates, and we're showing Rachel, like our collaborator, this, and she was like, oh, that's way suboptimal. So you have to be kind of control your errors properly, right? So once you do that, you basically show that the V1 direction matters, then what happens is now you look at U, Bn, and V1. And now you write out your Bn, unfurl this Hoeffding decomposition in there, T0, T1, etc., etc. Next step is to say that everything, this is actually 0. So let's not worry about that. Everything else is small. So that's kind of what you will have to bound. And the norm is dominated by the norm of this vector. And if you look at this vector, it's essentially of this form, which is eta over n times the sum of vectors which are not identically distributed, but they're independent. Okay, so for under some conditions, we can still say that this is roughly going to behave like a normal random vector. Okay, after I normalize, like scale it properly. So after all of that moving around and manipulations, you say that, oh, okay, so my sine squared error times n behaves roughly like norm squared of a normal random vector. Okay, and again, just giving you intuition, we can make all of this formal, plus small error. So that's where our distributional approximation is coming in. So that's theorem 1. I know it looks kind of complicated, but the thing to look at is here, which is basically saying that the CDF of the sine squared error properly scaled is going to behave like the CDF of the norm of a Gaussian vector for a suitably defined Gaussian vectors. Okay? And I don't want to get into details here, but this is essentially saying that behaves sort of like chi-squared. There are regularity conditions on moments of random quantities, and those are essentially, I'll talk about it in a slide, but those are essentially kind of coming out of variance decay, or the fact that I don't really have a high dimensional problem. There is some low dimensional problem hidden into this, because otherwise I won't be able to get rates like this. Okay, so, and also this learning rate is kind of has to lie between these two. So not the learning rate, like n times the learning rate. So here are the implications. The dimensionality can grow up to e to the power n to the power 1/3. Theorem holds for a very large range of eta. Now, previous work assumes that the operator norm of that quantity has to be bounded almost surely. And what we say is kind of higher moments of that quantity. It doesn't have to be bounded, can grow very slowly with respect to n. Okay, so it's slightly weaker, but sort of the same spirit is there. And finally, if we kind of translate our convergence result into an error bound, it matches the sharp error that Jain et al. Had. So we didn't really lose very much up to logarithmic factors. Okay, and the proof essentially adapts a result from Zhu et al., which is a high-dimensional CLT for quadratic forms, and they had identically distributed random variables. We have non-identically distributed random variables, so that's kind of where we had to do some analysis and so on. Okay, so this distribution and approximation, let's talk about Bootstrap a little bit. So I know that there is this distribution. How do I approximate it? Okay. So typically, Bootstrap consistency says that I have some unknown parameter. I'm estimating using some theta hat. This is the true CDF, and I'm going to approximate it by a Bootstrap CDF conditioned on the data. Right. So your theta hat becomes theta star in Bootstrap world. Your theta is plug-in theta hat. Now here it's slightly different from that because what we are saying is the theta hat is actually the estimator of error. So this whole thing, theta is just 0. So I'm essentially giving a distribution on the error itself. Okay, so the goal is to show this, where that thing, just think about that as the blue, the truth is the distribution of the sine squared error suitably scaled. And here it's the same thing. The only difference is the V1 is the truth. I don't get to see the V1, right? So I replace it with the Oja'S vector, which is all I have. It's my estimated thing. And V star is my Bootstrap replicate. So the question is, how do I build my Bootstrap replicates without calculating anything big? I want to just do online updates, just like Oja'S algorithm does. Okay, so the right thing to do. So now, so the goal right now is, before we calculated one Oja'S vector, you gave me one data point, I updated, you gave me another data point, I updated, and so on and so forth. Now I'm going to maintain B replicates, which are kind of like perturbed versions of the Oja'S vector along with the Oja'S vector. Okay. And the question is, each one of those replicates, how do I update them? I update them using online, essentially multiplier random variables. These are those Gaussian multipliers. The right way to do the update would be to take the expectation out here. So it's something like, oh, that should be an identity, sorry. So identity plus some learning rate times sigma, that's the expectation. And whatever mean 0 stuff was left, you will multiply that by a Gaussian multiplier. This is kind of the classical way of applying multiplier random variables to do Bootstrap. And you can see the I, that I is essentially the replicate. So I is equal to 1 to B. So at any time, you are kind of maintaining a drone of these Bootstrap vectors. Okay. Thing is, I went around, like, started by saying I don't want to calculate an estimate of the whole sigma, right? So this is really the right thing to do, but we don't really want to do that. So what do? So here is a fix. And the fix is, well, I don't know sigma, but maybe I can replace it. I have some very noisy estimate of it by XT transpose, some estimate of it. And then and what do I do here? Well, I do XT transpose minus XT minus 1 XT minus 1 transpose. Okay. The only thing is, the moment you do X minus Y of two IID random variables, you increase the variance by 2. So that's why you are scaling by 1 over square root. So that's kind of the fix. So this is completely online because it's essentially online by, like, you are remembering this step and the next step. So you need 2 data points. Of course, there is dependence. Now it's no longer independent. There is weak dependence, but as long as the norms are controlled, this weak dependence is manageable. And finally, the bad thing is it's not identically. I mean, the bad thing is not about this update. It's true for pretty much any multiplier Bootstrap type of thing. Before you had this beautiful identically distributed XT transposes, now you have condition on the data that times some multiplier random variables. So the ID, the identically distributed, is sort of gone, and you have to work much harder to sort of establish the results you did before, but it's doable. Okay. Right. How much time do I have? So here is our online Bootstrap algorithm. I draw U0 uniformly on the d-dimensional sphere. I am going to keep calculating my Oja'S vector because that's what I was doing anyway. And at the same time, I'm going to maintain B Bootstrap replicates. Each one of them is updated using this And the main quantity here is the ZTI, which is just normal 0, 1, standard normal multiplier random variable. Okay. So once I have that, I let it finish. I've seen all my data points. At the end of it, what I do is I calculate the sine squared error of each one of these guys with the Oja'S vector I have. So now I have B sine squared errors. That gives me the distribution. This is kind of very similar to what we do in Bootstrap. Right. So and we can basically show that Bootstrap consistency holds as well. So under the conditions of the theorem, and this is very complicated. So I'm just gonna tell you what this is. Again, some conditions on the norm. The norm cannot grow of the vectors. So this whole xi transpose minus sigma having bounded norm, this is kind of hidden inside that. It's basically saying that on that high probability set where things are not growing too fast, we should again have Bootstrap consistency. Okay. And when will the norms not grow very fast? When you have some form of variance decay. So there are conditions under which you can have those things happen. Right. So seems like I have time for some experiments. So I'm going to show you very basic kind of proof of concept type of simulation results. So I'm drawing some d-dimensional vectors and transforming them to have this kind of a covariance. And all you need to remember is that this is the variance decay. So if I make my beta super large, the variance decay is very quick. If I make my beta very small, it's flat. It shouldn't work. And we essentially do fix the initial U0, the initial vector, and then draw 500 data sets, run streaming PC and all of them. This is how we estimate the true CDF because that's what we are comparing with. And then we do the Bootstrap. Okay. Bootstrap replicates for a given U0. Now we are going to compare. That's it. That's all I'll show you. Okay. So, so here are two plots. This is for beta is equal to 1. There is quite a bit of variance decay. And the red is the true sampling CDF and the blue dots are the Bootstrap CDF. Okay. And you can see that they are sort of close. On the left panel, you have n about twice the number of dimensions. So D is large, but not that large. And then n is even larger. So here it's 20 times D. And you can see sort of that if I give you a lot of data points, this approximation gets better and better. That's what this is showing. And the next one again is just showing where variance decay doesn't happen, doesn't work. So beta is 0.2. The variance decay is, it's kind of very flat. And so what you are seeing here again is the two curves don't match. And more than that, the x-axis, the values here, because I'm basically plotting the CDF, the values are really large because things are not stabilizing. You are not converging to anything because that's essentially not the regime to be looking at. But if I, again, give you lots and lots and lots of data points, you'll start working there. So, yep, so that's it. So here in summary, there are lots of open questions here. We did something for Oja'S algorithm. Oja'S type updates show up in a lot of machine learning algorithms. So like, many non-convex problems like matrix completion, subspace tracking, and so on and so forth. And one interesting thing would be does these methods or ideas, do they transfer to those non-convex optimization algorithms as well? Can I do Bootstrap there? Can I have a distribution of similar sort of error? We did IID, random variables. What happens for weakly dependent streams of data? So say Markovian data or just weak dependence. And also top K principal vectors. I'm showing you something really simple, just the top eigenvector. What if I wanted to go to top K principal subspace? What happens there? So these are all things we are thinking about. And yeah, I'm gonna open for questions.
Really nice work. So one question, if you really truly want to be streaming, then your step size cannot depend on n.
That's right. Thank you so much. So what the thing is, if you make it 1 over t, then some of the conditions of CLT doesn't work because it's weighting different data points differently. So what we were thinking about doing was sort of doing it in batches. So, you kind of guess an n, you go with that n, and then once you exceed that, you double it and you keep going and so on. So that's
the chi-square. Did you try the chi-square approximation? Does it work well?
The chi-square approximation has so many, you need to, no, actually, the right thing to say is that I didn't, because it had all these model parameters that you need to know, like sigma, different properties of sigma, moments of it. So I didn't do that. But
so the chi-square parameters depend on all the other things.
Yeah, it depends on all the model parameters, like
Okay.
sigma and so on, and it's higher moments, xi transpose minus sigma higher moment. And so on.
Right. Thank you.
So it's scaled chi-square.
Oh yeah, it's scaled chi-square. Yes, yes.
Sorry.
Okay, I just wondered about the Bootstrap algorithm in Formula 3. I mean, you need to replace the sigma by an estimate, right? And why not taking from 1 to t minus 1 and only the last one, in Formula 3 on the right hand, 3, yeah, you have xt minus 1 transposed.
Right.
So this is a very noisy estimate of sigma, right? Why not going back to say x1 t minus 1 t minus 1 transposed? I just thought, okay, I mean, of course, I see what's going on here. I mean, roughly, but I would have taken a bit more information into account.
So you are thinking that maybe instead of this, take an average over. The trouble is so that's a great question. And it's a great question because it lets me get into this a little more. So if you look at this, I never calculate my xt transpose, which is d by d, right? So I'm always calculating some sort of a projection and so on. So if I keep averaging over t, okay, no, sorry, let me change that. So I think your scheme, I don't really need to calculate a d by d thing, right? I can still do like an online updated thing just by looking at t minus 1. It will be more accurate, but it will make the dependence much worse.
Yeah, that I understand. But I mean, there's maybe a trade-off to go back a bit.
We will try that. That's a great question. We didn't. We just went with one and it worked. But thank you for that. Yeah.
Thanks, Purna, for a great talk. So Peter asked the first of my two questions. You mentioned view statistics and you mentioned Hoeffding projection and Hoeffding decomposition. And so I was expecting the next thing to be some kind of a degeneracy or non-degeneracy condition, and it never showed up. Is that because you're already kind of looking at second moments, and like I expected there to be some condition that says that the Hoeffding decomposition, that leading order term dominates, that usually requires something like non-degeneracy with respect to.
That's a great question. So let me go back to that theorem really quickly.
Thanks.
So I hid a lot of things here. One of the things was something like you will need a lower bound on the variance, right? So that's your non-degeneracy condition right there. And that's sort of, I sometimes do this of like trying to make it more accessible, and I hide things that I shouldn't hide. Sorry about that, but thank you.
No need to be sorry. Just curious. Thank you so much.
The first principal component is easier. You comment at the very end. How about the second one? Any thought?
So the whole analysis of Oja'S, it works for top K, right? So all of these things. No, I don't know about the distributional approximation, but most of the theory works for top K. As long as there is a gap, it works. Like, gap between maybe 2 and 3, if there is a large gap, then 2 should work. So that's my feeling, that if there is a gap, it should be extendable. But yeah, I'm thinking about it. I haven't really worked it out.
Just a quick question. So is it possible to put a factor of lambda 2 on the numerator on the left side, because we know if lambda 2 is 0, the problem is trivial.
Ah. Right. I mean, yeah, that's my feeling is that maybe there was a lambda 2. I'll have to go check, but it's quite likely that we just abstracted it out because it's a constant, but I'll go check because that's a great point. Yeah. Yeah.
Thank you.
Other questions? Not, let's thank our speaker. Wonderful presentation. We now have a coffee break. I think outside again.